All right, welcome to 9.8 Power Series. So we're going to look at series that represent polynomials, okay? And how do we determine that? Well, this series has a variable x being raised to a power. So this actually represents a polynomial, all right? A sub n represents a number times x to some power, some number. This power series is a power series that's centered at x equals 0. So kind of similar to the Taylor and Maclaurin polynomials, where we're centered at x equals 0 or x equals c. It's going to look something like that when we write out our terms. This power series is centered at c. Okay, so it's going to look like this: some number times x minus c raised to some power n. And when you write out the terms, we get this polynomial, all right? But we're going to talk about the convergence, and we're going to talk about the interval of convergence. And in order to discuss that, the convergence, every power series converges at C since it's the center. So whether that's C or 0, okay? Now, there's kind of three types of convergence where it's convergent at just our center, our point, which means our radius is 0, which means if we took the limit of that series, we would get infinity, okay? We could have an interval of convergence, all right, where we have our center, C, and we have this R, which is our radius, okay? And we have this interval here, so R in this direction, R in this direction. So there's kind of four possibilities with this interval, okay? The four possibilities were it would be convergent on that left endpoint, but it diverges on that right endpoint. It diverges on both endpoints, diverges on the left endpoint, but converges on the right, or it converges on both endpoints, okay? So we would test the endpoints for convergence once we found our interval. Then the last scenario is where the series is convergent everywhere, meaning our center, we have our radius, which is infinity. So that would mean the limit of this series would go to 0. Okay, so notice kind of the difference between convergent at a point versus convergent everywhere. So what we need to do as we approach these power series to determine our radius of convergence, or our center and our radius, is we need to remind ourselves about the ratio test. Okay, so this is good for factorials and exponentials, remember, but in our case, when we're trying to find the radius and interval of convergence of a certain series, we're going to use this to determine where it converges, where it diverges. So remember, the ratio test converges when we are taking the limit as n goes to infinity of the absolute value of an plus 1 over an when it's less than 0. So this is kind of the big guy that we're going to be focusing on today. Then just quick reminders. The ratio test or our series diverges when that limit is greater than 1. And if it equals 1, it's inconclusive. But like I said, we're really going to focus on this guy here, all right, to help us determine the interval that we're looking at, the center and the radius. So let's go to our first example, and we'll walk through it. Okay, so if we want to find the radius and the interval of convergence for f of x equals this power series, if we were to write out the terms, when x equals 1, we would get x when when n is 2, when n is 3, 4, etc., etc. So we can see this is a power series. This looks like a polynomial, right, where our coefficients are going to be 1 over the square root of that n. All right, so the first thing we do is we need to find our center and our radius. So this is where the ratio test comes into play. We're going to use this to determine our interval and to determine our radius. So we set up our ratio test. The limit as n goes to infinity of the absolute value of x to the n plus 1 over square root of n plus 1 times the square root of n over x to the n. Cleaning things up, x to the n plus 1 over x to the n is just x, and then we can keep those guys over one another. as n goes to infinity, these guys just go to 1, okay? So they essentially go away, and we are just left with the absolute value of x. So based on the ratio test, we know that this converges when the absolute value of x, that limit, is less than 1, right? Because the limit as n went to infinity was the absolute value of x. So now we're just solving this inequality. So we can drop the absolute values, and we bring -1 over to the other side. So -1 is less than x, which is less than 1. So this is our interval, okay? Now, what's the center point between -1 and 1? That's 0. So our center is 0. So if our center is 0, what's the distance from 0 to 1? That's our radius. So our radius is 1, our center is 0, okay? These are the endpoints. So now what we need to do is we need to test those endpoints to determine if they are convergent or divergent at those points. So now what we want to do is we want to throw those endpoints in for the x value. So when x equals -1, we plug -1 in for the x here. And so what we have is we have this series, -1 to the n over n to the 1/2. So I notice it's an alternating series, so I test nth term is inconclusive. Now we look at the absolute value of that series, which is the series of 1 over n to the 1/2, which is a diverging p series, right? P is 1/2. So now we have to go to the alternating series test. So I take a look. The limit of that absolute value, right, as n goes to infinity, so we're looking at this guy here, is 0, so that works. And then we have to show that it is decreasing. So 1 over the square root of n is in fact greater than 1 over the square root of n plus 1. So it's decreasing, and that limit does equal 0. So this does converge conditionally by the alternating series test. So on our interval, I know I'm going to have a bracket at -1, okay? So now we still have to test the other endpoint, which is when x equals 1. So again, throwing that into the original series, 1 to the n over the square root of n, that just becomes the series of 1 over n to the 1/2, which is a diverging, you could say it's a diverging p series, or you can say nth term test, right? Either one of those works. So the interval of convergence, or as I call it, IOC, is going to be a bracket at -1, comma 1 with a parenthesis, because it converges at -1, but it diverges at x equals 1. Let's go to the next page and try another one on our own. Okay, so I want you to kind of try this guy on your own. I want you to find the radius and interval of convergence for this power series, -1 to the n times x minus 3 to the n over n plus 1. So first set up your ratio test and at least find your center and your radius. Then pause the video, come back and see how you did. Okay, so setting up the ratio test, the limit as n goes to infinity, x minus 3 to the n plus 1 over n plus 2 times n plus 1 over x minus 3 to the n. It's the absolute value of that. So cleaned up, we get the absolute value, or the limit of the absolute value of x minus 3 times n plus 1 over n plus 2. When we throw infinity in for n, these guys just go to 1. So we can essentially forget about that, and we are left with the limit equaling the absolute value of x minus 3. So we know that this converges when the absolute value of x minus 3 is less than 1. So solving this inequality, -1 is less than x minus 3, which is less than 1, and we get our interval of convergence, 2 to 4. Okay, so our center, what's the center point? Well, our center is when c is 3, our center, or x is 3. Our radius is going to be 1. Okay, so now I want you to pause the video again, and I want you to test those endpoints for convergence or divergence. So give yourself a little bit of time, try it, and then come back. Okay, so what we should have noticed is when we plug x equals 2 into our series here, we're going to get negative 1 to the n times negative 1 to the n over n plus 1. So we really have this series of 1 over n plus 1, which is a diverging harmonic series. So at x equals 2, we're diverging. At x equals 4, when we plug 4 in for x, we're going to get negative 1 to the n times 1 to the n over n plus 1. So we have ourselves this alternating series. So we throw the nth term test in. We're inconclusive. Now we're looking at the absolute value of that series, which becomes 1 over n plus 1, which is our harmonic series. This diverges. So now we're going to the alternating series test. So we're going to take the limit as n goes to infinity of that 1 over n plus 1, which does in fact equal 0. Showing that we are decreasing, 1 over n plus 1 is in fact greater than 1 over n plus 2. We would get 2 is greater than 1. So it is decreasing. Therefore, it converges conditionally, but that's not as important. It converges at x equals 4. So you should have gotten the interval of convergence to be a parenthesis at 2 and a bracket at 4. So here we have our final answer there. Okay? If you have any questions on this aspect, by all means, let us know. All right? And then one last concept here is just talking about derivatives and antiderivatives or integrals of power series. Okay? So if we have this power series where we have this polynomial, an times x minus c to the n, so it's centered at c, but where it's centered really doesn't matter. And we would write this polynomial out. Well, if we wanted to find the derivative of this, right, this a0 would go away. We'd be left with this constant a1, and we would bring the 2 on down. So we have a 2a2 times x minus c. We would bring that 3 on down, 3a3, x minus c squared, et cetera, et cetera, et cetera. So now we just want to write this back as a series. All right, so what we should notice is, what did we do? Very similarly to taking the derivative of anything else, we would just move this power on down in front, right? So it'd be the series from n equals 1 to infinity or n equals 0 to infinity, either one works, of n times an times that x minus c to the n minus 1. So that derivative hasn't really changed. If we look at the integral, we're very similar to the integral rules as well. So integrating this polynomial, we would have that constant, that plus c, plus this series from n equals 0 to infinity of that coefficient over the n plus 1, because that's what our power is going to go to. All right, so like I said, if you have any questions on these power series, let us know. Have a good day.